And I'll post these project ideas after they are approved by Professor Wang later on. So last class we talked about domain decomposition, overlapping domain decomposition methods, and a couple ideas, project ideas related to that. And the exercise that you did last night for today had to do with looking at additive Schwartz just with two subdomains. And one idea is to extend these Schwartz methods to multiple subdomains and to see what the convergence looks like. So the first idea is to look at multiplicative Schwartz for many subdomains. And multiplicative Schwartz was presented as a sequential method, applying the subdomain solve in one subdomain after another. But you can also parallelize the multiplicative Schwartz algorithm if you allow yourself to change the order in which you apply the subdomain solvers. Okay, so you can use multicoloring, for instance, to change the ordering. And in this multicoloring ordering, many subdomain solves can be applied in parallel. So this is analogous to the multicoloring idea that we had for ILU and for the resulting triangular solves for ILU. Okay? So another idea, so this one I just added at the last minute, has to do with two-level or in general multi-level Schwartz methods. So last class we talked about additive Schwartz, multiplicative Schwartz. These methods are generally not scalable, meaning that for larger and larger problems, the number of iterations will increase, just like the Jacobi and Gauss-Seidel smoother type methods that we saw before. And for these other methods, in order to make the methods scalable, constant number of iterations, no matter what the problem size, which you saw in one of these earlier exercises, you can also do the same thing by adding levels to the Schwartz and to these Schwartz algorithms. So the second project is to just add one level, so just to make the Schwartz algorithm a two-level method. And here the question is obviously, well, what is the coarse grid correction? What is the coarse grid? And you can imagine that you can have one coarse grid point for each subdomain. Okay, so and you can use a restriction operator that is a projection onto this coarse grid space, where the restriction operator is just an average of each one of these solutions on the subdomains. Okay, so that's another idea for a project. So other ideas for projects, I'll go through them fairly quickly. We did multigrid in one dimension. Well, it would be really cool to try multigrid in 2 dimensions or 3 dimensions, and I think it's not too hard to do by just changing the prolongation operator. And then once you have problems that no longer tri-diagonal, so tri-diagonal systems from the 1D case, they're really trivial to solve, then you can try more interesting smoothers. You could even try ILU and sparse approximate inverses, which you learned about earlier, as smoothers for multigrid. And this is really, really interesting because the ordering is going to affect the smoother, and issues like this are not very well understood. So really, these experiments are things that could be published as a poster or as a short paper somewhere. Okay, so an idea for using another project is to use the partition inverse algorithm. We traced out the algorithm in class, but no, I did not provide a MATLAB implementation. I have never actually implemented it myself, but I think it could be interesting to try it and to compare the number of partitions you get with the number of levels you get in level scheduling. And you can try it on just matrices from the University of Florida sparse matrix collection, which you have experience using. And you can also try using different orderings. So we saw that different ordering of the nodes can lead to more or fewer, hopefully fewer partitions. So you can try that as a project as well. We spent some time, a lecture on talking about partitioning, and interesting question is the comparison between regular graph partitioning using regular graph partitioning and hypergraph partitioning. And there is libraries for these things. As an example, you can use the METIS library and the HMETIS library for graph and hypergraph partitioning respectively. There are other libraries which were on the slides that I posted, and you can try those instead if you don't want to try these. And you can try them on different matrices and try to see whether or not, well, which one is better, or more precisely, how important is hypergraph partitioning compared to graph partitioning. Number 6, idea number 6. So we talked about a convection diffusion problem in class, simple discretization. It's the problem that had the beta in it. When beta is large, then the problem is convection dominated. And we didn't talk about this so much, but the ordering is really important when you're dominated by convection. So to see that, suppose that the convection is really, really large, then you can actually find an ordering of the matrix such that it is lower triangular. And in that case, you can think that there's that using Gauss-Seidel could be really, really effective compared to Gauss-Seidel in some other ordering. Okay, next page. How do I get to the next page? Oh, here we go. Okay, so you can try that. So 3 more ideas. We talked about how to compute the ILU pattern. So the standard way of computing these patterns is just to go through symbolically the Gaussian elimination process. But if you use the graph interpretation of level of fill for ILU, you can come up with a parallel algorithm for determining what the structure is. So that would be a very interesting thing to try to do. So using the graph interpretation of fill-in for level of fill, come up with a parallel algorithm for this. And the data structures, I think, will be very interesting. Like, to do this, you will require access to the matrix by rows or columns or both. So there are some questions about best sparse matrix data structures. Question 8 is also about triangular solves. And there's a relatively recent paper called sparsifying synchronization. So we didn't talk about this in class, but I think it is a very interesting idea. So you could read this paper and try to implement something and compare results. And then idea number 9, I've talked about this in class before, which is to compare RCM ordering with reverse breadth first ordering. And this, I think, nobody really knows the answers to this. So it would be very interesting to see what the results are over here. Any questions about these projects? And I'll let Professor Wang set the deadline for handing in the projects, some appropriate deadline. Okay, so today's our last class. There's assignment 2 due tomorrow, so students should submit either email or under Professor Wang's door, let's say by 2 o'clock in the afternoon. Is that okay? And assignment 3 will be posted tomorrow, again after Professor Wang's approval, and it will be about comparison between additive Schwartz and restricted additive Schwartz. It's a relatively shorter exercise or assignment because I know you're also working on projects starting the end of the lectures. Okay, so in our final lecture today, I want to go through a whirlwind tour of high-performance computing architectures and how to program these high-performance computers. So I know that some of you have some experience with this, but some of you don't, and I'll hope to say some things that will be interesting to all of you. View slideshow. Whoa. Okay. All right. So if you don't know very much about parallel computing, the landscape may seem very, very confusing, but I'm going to try to put some order into that landscape for you. But one important point is that there are many, many forms of hardware parallelism. Okay, so let's look at it one step at a time. So suppose you have a computer chip. I'm just going to call it a physical chip. And each one of these chips contains multiple cores. Each core can operate independently on programs. Okay? And each core itself can perform multiple instructions simultaneously. And this is sometimes called instruction-level parallelism. And each core can also have instructions that execute the same operation on multiple pieces of data simultaneously. And this is called SIMD parallelism. Okay, so we have a chip. It contains multiple cores. So there's parallelism right there, right? So it means we have to be able to use these multiple cores in a cooperative way to solve one problem. And then within each core, we have parallelism because we can execute instructions at the same time. So we have to make sure that we have enough parallelism in our algorithm so that there are instructions that can be executed at the same time. And in particular, this type of parallelism in which we might want to apply the same instruction to multiple pieces of data. Okay? So this is looking at a chip and going down, but you can also have many chips. So you could also have a computer that is networked, that networks together multiple nodes. Okay, so multiple compute nodes. And each node contains a system board, one or more chips, DRAM or memory, main memory, and also possibly coprocessors and accelerators. Okay, so coprocessors and accelerators, we'll see a picture in a moment. But in any case, here's a picture of a relatively recent Intel architecture. This is the Haswell architecture. So that's the chip, right? And this is a photograph of the chip. And you can see that in this picture there are 4 cores, okay? And there's also some additional processing units here that are specialized for graphics, okay? So I think this picture is really good if you've never seen anything like this before. It really emphasizes the fact that in one of these chips you have these multiple cores, okay? And also on this chip is cache, and we talked about cache a little bit before. This is where you store recently used data so that it can be accessed by the cores very rapidly. Instead of having to go off the chip, so here are some pins that go off the chip to main memory, which may take a long time. This really emphasizes the fact that the cache is on the chip. You can access this memory much faster. It's also much faster logic, okay? And if you look really closely, these things over here are other levels of cache. So level 1 cache and level 2 cache over here, which you can access even more rapidly than L3 cache. So here these caches are private to each core, and here this L3 cache is shared between among the 4 cores. Okay, so this emphasizes some of the stuff that is going on. And remember, the processing units could be using SIMD processing as well. Okay, so coprocessors and accelerators. So here's Intel Xeon Phi. It's a thing that plugs into your main board. Okay, and the processor would have to, and it communicates with the processor through an interface called the PCIe interface. Okay, similar for GPUs, it plugs into the main board and it communicates through these pins and the PCIe interface. We'll see a little bit more about Intel Xeon Phi later in today's lecture. And how would you build a cluster computer? In other words, you have a number of nodes. You have a lot of money. You bought a whole bunch of nodes. This is a do-it-yourself version. Okay, so you buy a whole bunch of these computers, and the important thing is you have all of these computers, and they're all networked together over here with this network switch. Okay, network switches. This is all networked into a single network switch, they're quite expensive components, especially if you want the communication to be really fast. If you're downloading lots of movies, for instance, but of course you're not downloading movies here on this machine. So this is a do-it-yourself version. A more modern version is something that looks like this. So this is a small cluster that we use for instruction at Georgia Tech. So these clusters are composed of a number of cabinets, and within each cabinet you have these blades, and within each blade you have one or more of these processing of these nodes. So each one of these boxes would correspond to one of these blades in these cabinets. And you can see again lots of wires to connect all of the nodes together through some kind of network. Okay, so an important concept, so important I actually say important concept on the slide, and this really helps you organize your thoughts about parallel computing, is that there's two main types, and the main types depend on whether or not memory is shared or memory is not shared. In the not shared case, it's called distributed memory. Okay, so in this case, there's a memory in each one of these boxes, right? Or in this case, there's memory in each one of these boxes. And if a program is using all of these compute nodes to cooperatively do one computation, in order to access the memory on some other node, you have to do something special. Okay, you just can't read the memory directly using an address like you would in the shared memory case. So these are the two main cases, shared memory and distributed memory. Okay? And we're going to talk about these in different ways. So some people say that distributed memory computing is a lot more, programming is a lot more difficult. Some people say that shared memory programming is a lot more difficult. I can have a very long discussion with you about why this may or may not be the case, but we will go on and maybe you can decide for yourself. But besides the parallelism, the other important aspect to consider is data access. So data access time, as I may have mentioned in an earlier lecture, is really could be a bottleneck, and especially in sparse linear solvers, which has been the topic of this course. It could be the bottleneck because the ratio of communication to computation is quite large in these types of computations compared to other types of computations. So when we're talking about data access, we're talking about data access across the nodes or between the nodes, and also to main memory. In other words, from CPU all the way to main memory, traversing various levels of cache. And data access can be measured in terms of bandwidth and latency. And actually, it's a combination of bandwidth and latency. So we'll talk about bandwidth first. Bandwidth is just how fast memory or data can be delivered, let's say, to a processor. And you can measure this, for instance, using several different types of benchmark codes. This one is called the stream benchmark, very well known. Okay, so you just take a very simple operation like adding two vectors together. So you can see that the amount of communication or data access is quite large. You need to access all of C, all of B, and then you have to write back the result into A. That's quite a few things to read and write. And you're only doing one flop for each of these three elements. Okay, so whenever you're doing something like this, you're going to be limited by how fast you can read memory, not how fast your computer can perform arithmetic. Okay, so this is why it can be a bottleneck. So this benchmark measures things like this vector operation. Okay, and it's good to know what the maximum bandwidth is because it will tell you how fast your program can go, assuming that your program is limited by memory bandwidth. Okay. The other thing, memory latency, how does that contrast with bandwidth? Well, latency is the time for starting up a memory access. So if you want to start reading some data from a certain location, it's going to take hundreds of computer cycles. Okay. But if you want to read additional words, then that's going to be related to the bandwidth. So it might take 3 cycles to read additional words. So you want to read words, you want to read data, for instance, in contiguous chunks to reduce the average time for reading these words. So you want to read them in large chunks, or we refer to them as large memory transfers. So the time you can think of for reading some data depends on the length of the amount of data you want to read. It's going to depend on latency, which is just a startup cost. It doesn't depend on the length of your message, and then how long it takes to read all of the words. Okay, so memory performance, very important aspect in high performance computing. So how do we handle this really long startup time? So for instance, in this previous computation, if we had to wait hundreds of cycles just to read one element, right? And then we perform one addition, that takes one cycle. Then we wait hundreds of cycles again for the next element. So that would be really ridiculous, right? It would be, our computing would be really, really slow. So there's two solutions to this problem. One is cache, which you already know about, right? The idea is that you organize your computations in a way such that once you've read in the data, you put it inside cache, and access to cache is really fast. So you don't have to wait these hundreds of cycles for DRAM latency, okay? And also in this case, there's some prefetching that will speed things up. So that's the idea behind using cache. And the other idea is to use multi-threading. And the idea there is you have multiple things trying to, multiple computations going on at the same time. More computations than you have cores. So when one thread or one thread of execution is requesting memory and has to wait possibly hundreds of cycles, then it will get stalled, and another thread instead will go onto the core and do some possibly useful computation. And when the memory is ready, then this thread comes back to the core and does the computation. So by using multiple threads, you can hide the latency. And this is the main idea behind GPU computing, where you have a large number of cores, but you have an even larger number of threads that have to execute at the same time in order to hide memory latency. So two main ideas. In CPUs generally have large caches. Okay, so if we go back to this picture, you see the cache, the area it takes up on the chip is relatively large. And you can imagine that if we didn't have to have all this cache, we could have bigger cores or even more cores to do more work. But here we want to have more cache. On GPUs, the picture is very different. We have a very small amount of cache and we have lots of cores. And the way we handle memory latency is to use multi-threading or hyper-threading or whatever you might want to call it. Okay, so going forward. So here's another picture. Here's another picture of a processor. I think this is a Nehalem. And I like this picture because you can really see this one has 4 cores. You have L3 cache. I think these are shared, even though there's 4 banks. I think they're shared. And then there's L2 cache in here, level 2 cache. And then there's also level 1 cache. Okay, there's level 1 cache for data and level 1 cache for instructions. Okay, so you can see that there's 32 kilobytes of this. So it's less dense, but it's much faster. So this is even faster than level 2, and level 2 is much faster than level 3. And this picture says, well, this is the typical picture that illustrates a memory hierarchy. The CPU accesses memory through these different levels of cache. The higher the levels, they're faster, but they're also smaller. Okay? So at the lowest levels, you have perhaps DRAM or disk, which is quite large. Okay. So processor level SIMD, which is something I just introduced a moment ago, this is what I want to talk about now. It's an instruction that can perform an operation on multiple words simultaneously. Okay, so before SIMD, and this is the way that you would normally think about things, you just think about scalar instructions. You have an X, you have a Y, and you want to compute a product. Okay? If a SIMD instruction, you have 4 values of X, and you have 4 values of Y, and you're going to compute 4 values of the product. using the same instruction. Okay? And it does it at the same speed as doing that. So if you want your computation to go fast, you want to use instructions that look like this rather than instructions that look like that. Right? The main question is whether or not you have in your code or in your algorithm an opportunity to use instructions like this. So if all of your computations are scalar computations, then you're not going to be using instructions like this. So it's very hard sometimes to take sparse matrix algorithms and to reorganize them in a way such that you have, you can use these long vectors. And the idea of trying to use these long vectors is exactly the reason why in our lecture on sparse matrix data structures, we changed from using compressed sparse row to things like LPAC format, which allows us to use much longer vectors and allows us to use SIMD instructions instead of using scalar instructions. Okay? So let me explain the term SIMD. A long time ago, these terms were introduced, and you can think of parallelism in the instruction stream. So we have single instructions and multiple data, sorry, single instructions or multiple instructions. And you can also think of parallelism in the data stream. You have single pieces of data and you have multiple pieces of data. So the simplest idea, the simplest concept is you have a single stream of data and you have a single stream of instructions acting on that data, and that's called single instruction, single data, or SysD. Okay. And then at the other extreme, you have multiple streams of data and you have multiple instructions, like multiple programs operating on these multiple streams of data, and that's called MIMD. Okay? And then SIMD is the case where you have multiple streams of data, like these 4 streams of data, and a single instruction acting on it. Okay? And SIMD, you know, vector supercomputers were also SIMD machines in a way. So this is what SIMD means, single instruction, multiple data. This MISD case, single data stream and multiple instructions, that's kind of interesting. Are there any computers that do that? So maybe not. But you can imagine what this might be. So for instance, suppose that we're 50 years into the future and you know how all of your data is being collected and analyzed thoroughly by companies and governments, things like that. So you have one stream of data, all your purchases on Amazon, or all of your telephone calls, whatever. And then you have multiple pieces of hardware acting on the single stream of data. So that is conceptually something that would be MISD. Okay, so getting back to regular SIMD, so through different versions of the Intel microarchitecture, okay, so we have Skylake now, but I don't have too much information about Skylake. Actually, my laptop uses that, but it's not a server laptop. So in any case, we have different SIMD versions. We note that the versions are not backward compatible, but you can also see that the width of SIMD instructions is increasing. So 128-bit, so each double precision word is 64 bits. So this could do 2 double precision computations at the same time, or maybe 4 floating point, single precision floating point computations at the same time. But you can see that the width has increased very rapidly in recent years. This is because it's relatively, you can get a lot more performance by increasing the SIMD width if you're able to use, let's say, 8 streams of data at the same time. And this is a way of these processor companies to provide you additional compute capability, hoping that you can use it. So if you can't use it, then you're kind of stuck because you're really underutilizing this hardware. Okay, so how do you actually use SIMD? Well, the good news is hopefully you don't have to pay attention to it because the compiler does this for you automatically. You write a program, and the compiler will automatically insert instructions to perform and reorganize your computations to perform, to use these SIMD instructions. Okay? Sometimes the compiler doesn't do this perfectly, so you might want to insert your own assembly code. This is a very low-level way of doing things, really only suggested for Ninja programmers. And another way is to insert some things called intrinsics, which are just instructions that you can insert into, for instance, your C code, which map to assembly instructions. And if the compiler doesn't do what you want, then you can do this. So a lot of people are doing this these days. It's kind of fun to do it because you get a little bit closer to the hardware. So here are some examples of SIMD intrinsics. So you have some data types. Let's say this is for SSCs, so 128-bit single precision, double precision data types, and then you have these instructions like load and adds that are these SIMD, that map to SIMD instructions. Okay? So a couple comments about processor level SIMD. One is that if your code is memory bandwidth bound, then using SIMD will not help improve performance. Right? So if your sparse matrix vector multiply is limited by how fast you can read the matrix A and read elements of X and maybe write out elements of Y, then using SIMD is not going to help. So so this is where it's useful to know what the bandwidth capabilities of your machine are compared to other capabilities. However, on things like GPUs, there are so many other things that slow down computation that you might not be using the full memory bandwidth, and SIMD then does help. So on GPUs, for instance, you really have to use SIMD. Another interesting thing about SIMD is that it shortens your code because you have fewer instructions. So you might reduce the memory bandwidth for instructions, and since memory bandwidth is so important, then this could be an important consideration. Okay, so now we'll move on to how to program away from SIMD to how to program multiple cores. And the simplest way to do this in scientific computing is to use something called OpenMP. And it is a way of programming multiple threads in a very natural way that share the same address space. Okay? So this is simpler than using POSIX threads. If you're in computer science, you may have heard of using POSIX threads. It's a low-level way of accessing, using multiple threads, using multiple cores at the same time. And OpenMP you can think of as being built on top of POSIX threads. And there's quite a bit of documentation on how to use this on the web. And there's very easy ways of doing this. We saw an example with the sparse matrix vector product MEX code that I showed you several lectures back. We had a main loop over the number of rows, and we just added one compiler directive, some compiler directive, not exactly this one, but similar to that, that just said within this loop, just parallelize using multiple threads. Okay, so if I could jump ahead to maybe this picture. So these are loop iterations, right? By putting a compiler directive in front of that loop, then it says, well, the first 7 loop iterations assign that to the first thread, which will run on one core. The next 7 iterations assign that to another thread, run on another core, etc. So this assumes that these iterations are completely independent. And in the case of sparse matrix vector multiply, computing each element of the result, if you have a row-wise distribution of your row-wise representation of your matrix, that is an independent calculation. And you can also tell OpenMP how to schedule your threads. And this is important if, for instance, some rows are longer than others. That means some threads might do more work than others. So you might want to break things up into smaller chunks or to schedule them dynamically. So first, each item will be assigned to each thread when the first thread is done, it gets the next thread. Second item is done, it gets the next thread. But the third thread is still really busy. It's not done yet, but the first thread is done again, so it gets the next item over here. So this is a dynamic type of scheduling. And you can also combine dynamic with a chunk size. And you can also use something called guided, because you don't want your last chunk to be really large. That means your last thread works on something really large while all your other threads are done. So that's a load imbalance. So guided means that we're going to start off with large chunks, and then the chunks get smaller, because then hopefully all of the threads will finish at the same time. So various things like that in OpenMP to give you an idea more about what can be done. So the programming is primarily through inserting these directives into your program, right? And these are some of the directives. I think the most useful directives. Okay, so you can say that one section of your code is a critical section. Only one thread can access that section at any single time. There's some clauses which modify the behavior of those directives. And then compiling an OpenMP program, you have to tell it to link to the OpenMP library, your compiler to link to the OpenMP library, and to recognize the directives. You can set the number of threads as well in different ways. Okay, so there is some cost to using OpenMP, and that is when you create threads, there are some overheads. So you have to be aware of that, just like if you were using POSIX threads. Okay? Scheduling the threads may involve some overhead, and there are different implementations of schedulers, some of which are more efficient than others. But in any case, the concept I want to point out here is that if you have 8 threads, you cannot expect your program to always be 8 times faster than if you use a single thread. Okay, so that's the important concept. And the reason for that is because of these overheads, and there could be other issues such as conflicts in shared caches. You may be limited by memory bandwidth as you use more cores on your machine, right? So there are many reasons why you might not get a perfect speed up when you use, let's say, 8 threads compared to a single thread. Okay, so I think I said some of that already. Okay, so now let's move on to message passing interface. So we talked about shared memory programming very, very briefly using OpenMP. And now we'll talk about when the other form of parallelism in which you have memory that is distributed. And in that case, you cannot just read memory directly. You have to use, you have to do something special to access memory that is located on another node. And the standard way to do this these days, there are many ways, but a standard way is to use something called the message passing interface. So it's an interface that was designed for portability. So if you imagine 20 years ago, or maybe 25 years ago, before MPI, different networking companies would produce their own network hardware and produce some software libraries that say if you want to exchange information between different compute nodes using our network hardware, you have to use our network library. And this would mean that if you decide to move your program to another computer that uses a different network, you would have to change your program. So there were a lot of difficulties like this in the early days. And the idea behind MPI was to get all these vendors together and say, well, let's all agree on one message passing interface that everyone can use so that people who program to this interface do not have to change their programs whenever the hardware changes. Okay, so message passing interface refers to that interface, and many people have developed implementations of these interfaces. Primarily companies, but also national labs have developed implementations called MPI that people can use. Very widespread use. We do not anticipate MPI going away. And as I said before, there are other options, but this is one of the main options. And if I were to teach one thing about distributed memory programming, it would be MPI. So MPI, it has grown over the years. But at the beginning, people thought of MPI as being something that could be potentially easy to use, because you really only needed 6 functions to understand, to do the most basic things, although in practice you actually have to use a lot more. So you have to, for instance, initialize the MPI library at the beginning. You have to finalize the MPI library at the end. You have to know how many nodes are trying to communicate with each other, so the communicator size. You want to know what is your rank or your identity inside among all of the processes communicating. So if there's 8 processes communicating, each one would be labeled from 1 to 7. You want to know which one you are, so that you can assign yourself some work that is different than other processes. And then 2 basic things for actually performing the communication: sending some data from one node to another node, but also explicitly receiving data from another node to your node. Okay, so send generally says, well, here's some data. And receive will say, well, I'm ready to receive some data, and when I receive it, I want to put it here. Okay, so this is the basic way of doing communication in MPI. It is synchronized. It's 2-sided because the sender and the receiver are both aware of the communication. There are many other functions. For instance, there's one-sided MPI in which one node will send to another node without the other node knowing about it. And in order to do that, there has to be some setup at the beginning, which is a little bit more complicated, that says, well, if I send something, where will it actually go on the other node? So the nodes have to kind of agree on that first. But once they agree, it's very useful because the other node does never have to know if this first node wants to perform some communication. And that can be very useful in some cases, in cases of algorithms where it's very difficult to predict who wants to communicate with you. Okay, so this was called point-to-point communication. So communication between one node and another node. And the second most important type of communication, so this one-sided is not one of them, it's maybe the third most or something like that, is something called collective communication. And this is where multiple nodes might communicate with each other at the same time. So to give you an example of the send and receive, so an MPI send, so if you've used MPI, this is familiar to you. In this case, we're talking about the blocking send and receive. So MPI send will specify a buffer that contains some data that the node wants to send. Okay? And the function will not return until the send buffer is available to be used again. But it does not mean that the message has been sent. It just means that the message has been safely put somewhere and it may be sent at a future time. Okay? And then MPI receive, the blocking version says, well, I'm going to wait for a message that I'm expecting, and I'm going to wait here until I receive that message. Okay? So if we use blocking send and receive, we have this very interesting case that this piece of code, this running on one processor and this running on another processor, so this running on processor 0, this running on processor 1, this will actually deadlock, because this will wait until the message is sent, until the send buffer is available, and this will wait until the send buffer is available. Okay, but so they're both waiting, and they could both get stuck here before these receives are posted. So an easier way of doing this is to use something called non-blocking send and receive. So a non-blocking send will return immediately. Okay, and you can do other things such as computations. But you should not touch your send buffer because the data that you want to send is still there. You don't want to overwrite that send buffer. Okay? MPI I receive, similar, it says, I'm going to I'm expecting a message to be sent to me. This is where I want the message to go once I receive it. But instead of waiting for the message, I'm going to allow this function returns immediately. Okay, and you can do other things, but you can't overwrite your receive buffer in case the message arrives before you find out and then write something to it. So these functions are coupled with an MPI wait that actually does the waiting when you are actually ready to wait for the send to complete or the receive to complete. Okay, so these non-blocking versions allow you to overlap communication with computation, easier to avoid deadlocks, such as the example that we saw in the previous slide. Okay, and here's a plot of the time it takes to send a message between two different nodes. So this is time on the y-axis, and on the x-axis is the message length. This was done a number of years ago. This is just a blow-up of this smaller portion. So you can see that for a very short message, this is the amount of time. So maybe about 2 microseconds. And up to even 10 bytes, so this is size in bytes, even up to 10 bytes, it still takes 2 microseconds. And this is because of the large latency, the large startup time for sending a message. And then only after the message is quite large do you start to see the time being dominated by bandwidth. Okay, where if you send a very large message, then the latency time is no longer important. Okay, you can see this non-smooth behavior over here. This is a very interesting artifact, and it's the result of the MPI implementations changing protocols. It sends messages in a slightly different way if you have a short message or a long message. It's called the eager protocol versus the rendezvous protocol. If you have a short message, the message is just sent immediately. We don't worry about whether or not the receiver has already said, well, where to put it, because the receiver is just going to put it somewhere and then eventually copy it to where the MPI receives said to put it. So that's the eager protocol. And the rendezvous protocol, if you have a longer message, you can't do that because there's no guarantee that on the other side you have space to store the message. So you have to first send a short message to say, are you ready to receive my message? The receiver sends back a message saying, yes, I am. And then you actually send a message. So it's a longer, it's a three-stage protocol. So the protocol changes, very interesting to see what happens, even in this case over here for very, very short messages in these different implementations. So in terms of collective communication, this is where multiple processes are are communicating simultaneously. Okay, so this is a set of common collective operations, and these are some pictures of collective operations. So if you're not familiar with MPI, this gives you an idea of what can be done. Okay, so suppose you have 4 processes, 0 to 3, and process 0 has some data. The broadcast collective operation just says this data is sent to all of the other processes. So this could be important. So for instance, processor 0 might read a file containing all of the input parameters. All the other processes need to know what the input parameters are, so you just broadcast it. So that's one use of broadcast. So here's scatter, where a process has some data, and it wants to send the data to all the other processes, but all the other processes just need one part of it. Okay, so for instance, process 0 could store, for some reason, the entire matrix. Okay, and you want to do a sparse matrix vector multiply, but each process only needs some of the rows. It's not going to store all of the rows. So this is where process 0 scatters some of the rows. Okay. Gather is just the opposite. Suppose you have a solution that spans, a solution, let's say X, that spans the entire set of processes, but you want to print out the solution. So you could gather all of them onto one node, and then one node just prints out that solution. So those are examples of scatter and gather. And then there are other things like all gather, okay, all to all, okay, Reduce, this is very common because you might want, this is the backbone of inner products. So for instance, you're running the conjugate gradient method, right? So this is components of a vector, and you want to compute the inner product, or you want to compute a norm. So you want to compute a norm of a vector that is distributed across multiple processes. So that would happen using some kind of reduction. You know, you add all these together and it brings it to one of the nodes. Scan, there's some others as well. Okay. Okay. Any questions about MPI? Yes.
Developing environment or other kind of tools.
Okay. Yeah. So debugging parallel programs is very challenging because you have a lot of processes or a lot of threads working at the same time. And there are some debuggers that are available for doing that, but they're not necessarily effective. So in terms of advice, I don't know if I have any particular advice. I can tell you what is available. If you want something that is free, you can use just GDB running on different processes, right? So that's the simplest way to do things. It might be okay if you don't have too many processes. If you're trying to debug something, you want to try to reduce the problem to the smallest instance, smallest number of nodes, smallest problem size, and hopefully the bug still appears, and then you could use something like that. There are some products like TotalView that I've used in the past for debugging parallel programs. I haven't used it recently, so I don't even know what the state of that is. Okay, and then Intel also has some debuggers that can work, especially in the shared memory case. When I talk to people, what I hear very often is that they think the easiest thing to do is just to use printfs, which means just to put some print statements in your program to try to tell you what is going on. And that is sometimes a lot easier than using a debugger. As an instructor, I always try to tell students to at least be familiar with debuggers so that you know what they're capable of doing, because sometimes in certain cases they can really help you. Like if you need to step through a program, if you want to instantly find where a segmentation fault occurred, debuggers are very, very useful. But when you have very, very complicated programs, sometimes printfs do help. You have to be aware that printfs might not always occur in the same order because prints are sometimes buffered. So I don't have any specific advice, but my advice maybe would be aware of debuggers, and then be aware of your other options. Okay. Any other questions? Okay, so now we'll move on to something called non-uniform memory access. And this is a much more subtle issue that some of you may not be aware of. And this is abbreviated as NUMA. And it's the concept that memory access between your processor core to main memory is not uniform. Okay, so if you want to access some memory, sometimes it might take so long, sometimes it might take much longer. Okay, so it's not uniform, and you'll see why this is the case very precisely. But in general, why it is the case is because memory is located in separate regions called locality domains or NUMA domains. Okay, in other words, all of the memory is actually not just in one place. It used to be all in one place, but it's not all in one place anymore. So conceptually, we just think of memory as being out there. We want to access memory. It should take the same time every time we go, right? We need memory. And for highest performance, your core should only access memory that is in the nearest NUMA domain. Okay, so what does all of this mean? So to explain NUMA, I like to go back to a time before 2008, before memory was non-uniform. So in a time where memory access was uniform. So this is what your computer looked like before 2008. You have a processor, right? And you have memory slots. So these are slots in which you would insert memory if you ever went to a computer store to buy memory and you want to insert it. So these are memory slots. Okay, and then there's a memory controller, which is called the North Bridge. It's a chip that is the memory controller. And if the CPU wanted to access memory, it would go through the North Bridge. And you can see that, no matter what memory you're trying to access, it's the same path to go to memory. And the North Bridge also was how you would access your graphics card, for instance. And if you wanted to access other peripherals, you would go through another controller, the I/O controller called the South Bridge, and you would have things plugged in here. An old peripheral might be a modem, for instance. It could be something else. Okay, so these were 3 different chips on your machine. And if you look at one of these pre-2008 motherboards, okay, so this is what it looks like. And I think this picture is also very instructive. So here is where your processor is inserted on the board, okay? And near it is the North Bridge processor, okay? And here are the slots for the memory. So you can see that it's a relatively short distance on the motherboard. If the processor needs to access memory, it will go through the memory controller, then it would access the memory over here. And here's the South Bridge. And the South Bridge is connected to these PCI slots, which are connected to your slower peripherals. If the CPU needed to access something that's on this interface, then it would go through the North Bridge, the South Bridge over here, and then back again. Okay, so this is pre-2008 picture. All right, so now what do we have? So AMD invented something called Hypertransport, and then very soon after, Intel came up with something called the QuickPath Interconnect. And it was really designed for situations in which you have multiple chips, or at least the case of multiple cores. Okay, so here's 2 pictures basically of the same thing. So now we have 2 processors. Okay, they could be, imagine it as being 2 chips. Okay. The memory controller is now on the CPU. So there's no more North Bridge. What the North Bridge used to do is actually on the CPU. And as a result, this CPU can access memory directly. Okay? And then this CPU, which has its own memory controller, can access memory directly as well. Okay? And this I/O thing is really the new South Bridge. So here's another picture of the same thing. You have 2 processors. Each one has its own memory controller, and it can access memory over here. This processor has its own memory controller and can access memory over here. Now, here's the question. If this processor wants to access memory over here, then it has to go through the QuickPath Interconnect. It has to go through these things, QPI. So you can see that access to memory over here by this processor is a lot faster than access to memory over here. So this is what leads to memory access being non-uniform. Okay? So I like this idea so much. I have so many different pictures that I've taken from the internet. So this is the previous generation, multiple CPUs going through the North Bridge, accessing the memory. It's all uniform. So here's an example with 4 CPUs, NUMA case. Each one has direct access to its own memory. And in between is the QuickPath Interconnect. If this CPU wants to access memory over here, it has to go through that interconnect. Okay? So why did people invent NUMA? Well, to give us a hard time. Also, if we're high-performance computing people. But also, the reason was so that we could get higher memory bandwidth to memory, higher bandwidth to memory. So remember I said earlier that access to memory could be a bottleneck. So vendors are working hard to try to figure out how to give us more bandwidth to memory. Okay, and this is what they came up with to use to place the memory controllers on the CPU, more direct access to memory. So you can imagine all of these CPUs can be accessing memory at the same time. Let's say accessing memory that is most local to them, and you can get really high memory bandwidth this way if your computation was organized this way. So you can see that you can get really high memory bandwidth, and the trade-off here is that you have non-uniform memory access. Okay, so you have to live with possibility of non-uniform memory access. And you can observe these NUMA effects, writing programs in which you access memory somewhere else that's a farther memory domain versus a nearby memory domain. And you can actually see what the structure of your machine is. So if you go onto a heavy-duty server that has lots of cores, or lots of sockets, let's say it has 4 sockets, lots of processors, you can actually use this command to see what the NUMA structure is. In other words, see what this network looks like. How many hops it takes from one NUMA domain to get to another NUMA domain. Okay, so if you're writing a program, how do you know where your memory actually is? So how does the operating system decide where to put your memory? Where to put your memory? Okay, so here's a couple of references for more details. But the idea to know is that memory is located by first touch. Okay, so when a thread on a core on a processor allocates memory, that's not when we decide, or that's not when the operating system decides where that memory will be located. It's when you access that memory for the very first time, depending on where you are, that memory will be put in the locality domain that's closest to you. Okay? Now, if for some reason your thread moves to another processor, then you will be accessing memory in a farther memory domain. So it's important then to make sure that all of your threads stay locked onto the same core or the same processor, and that is called thread affinity. Okay, so you can set how pages are placed this way using this memory control, NUMA control function, as well as to just see what it looks like. And thread affinity is that you want threads to be locked or pinned to cores. And if you don't do it, the default is that they can move to different cores, in which case, the local caches on those cores might not be the information that you want. Your NUMA domains, you might not be closer to the NUMA domain that contains most of your data. And there are ways of trying to control all these things. For instance, on Intel compilers, there's this KMP affinity environment variable that you can set to tell to specify the behavior that you want. Okay, so let me talk now about Intel Xeon Phi coprocessors. So I won't talk about GPUs because I think a lot of you already know about GPUs. I work with Intel, and one of the things that we do is to try to develop codes for these coprocessors. We have a lot of these, in fact. If you want an account on one, I'm very happy to give you access to ours if you want to experiment with these things. And there's a very good book that describes how to use these things. So that's this reference over here. So this is what conceptually a Xeon Phi coprocessor looks like. So remember, it's plugged into basically the graphics card, the PCIe interface on the motherboard. Okay, so it has to go through not the I/O controller. I guess it doesn't have to go through. Let's see where it goes through. So it does have to go through the I/O controller. Okay. So it's a little bit slow because of that, and I'll mention that again in a moment. But it's a coprocessor that has around 60 cores on the chip. These cores are not as powerful as a regular Xeon, let's say Intel Xeon CPU core. Okay, so they're relatively weak cores. They're connected via a ring bus on the chip, which is not ideal because it means that communication across the ring can take a long time. It has enough cores and enough flop rate to reach 1 teraflop of double precision computation. So that has been demonstrated. And these are x86 cores, so they're compatible with x86 programs that have been generated for who knows how long. In contrast to GPUs, in which you have to write new code. Okay, and each core has 512-bit SIMD units. Okay, so you have to use these SIMD units in order to be efficient. So let's take a look at this picture again. Okay, so here's the ring bus. There's multiple cores on the ring bus. So this picture only has 8 cores, but in reality there's about 60 of them, right? And each core, when it's trying to access memory, will go through its L1 cache, then its L2 cache. And the L2 cache is distributed, and there are tag directories that tell cores where data resides in L2 cache. And if you want to access main memory, your request goes to one of these memory controllers also on the ring bus out to main memory, which is on the card, okay, on the card that's in here. So it has some main memory, something like 8 or 16 gigabytes of main memory. Okay, and so the request will go out and then come back. Okay, and also it would go out this way if you needed to access data in the main memory of your compute node through the CPU. Okay.
So, can you say what was it? Technically, it's a NUMA?
Yeah. So there's a lot of argument about whether or not this is an architecture that is non-uniform memory access. And I think that it is slightly non-uniform because depending on where you are on the ring bus, right, you can take 1 or 2 extra hops to get to a memory controller, right? So it's a little bit non-uniform this way. But the people who design these things want to call it uniform memory access. Maybe it sounds nicer. Or maybe because the difference is so small, it's really just a difference of a few hops before you get to a memory controller. So that's accessing main memory. They want to call it uniform memory access. But also, if you want to access L2, then you could take a very different number of hops depending on where the data actually is, which L2 cache is actually in. So in that case, the L2 cache is access L2 cache is very non-uniform. Okay. All right. So because we have these really wide SIMD units, codes that run on these processors really have to use these things efficiently. There are ways of using Intel compilers to tell you how efficiently you're using vectorization. Okay. So this slide shows you how important vectorization is on the Intel Xeon Phi coprocessor. So take a look at this example. We have a scalar code. It's using 1 core, and we're comparing in this first bar just an Intel Xeon CPU and an Intel Xeon Phi coprocessor. So if you're using a single core and you're not using SIMD instructions, the coprocessor core is slower. Okay. Now if you're going to use SIMD, still on a single core, the coprocessor core is almost as good, but still slower. Okay. Now if you're using for this case, you're using a scalar code, in other words, no SIMD, but you're using all cores, which I think is 20 cores on this thing. It's a dual socket, so 20 cores in total, and 60 cores in total on this one. You can see that the Xeon Phi is now just a little bit faster. And then if you use SIMD and you use all of the cores, so this is the full capability of this dual socket CPU system and of the coprocessor, you can see then the Xeon Phi is more than twice as fast. So you have to use all of the cores and you have to use SIMD in order for these coprocessors to be effective. Otherwise, you should just buy one of these Xeon CPUs and you would be fine. Okay, so this tells you there's quite a bit of challenge in trying to adapt codes this way. So this is a picture of memory performance, same two systems. So the stream triad is that benchmark of adding two vectors together. You can see that the memory performance is much higher for this Xeon Phi than for the Xeon CPU. However, if the memory access is not very regular, if it's random with 4 kilobyte size blocks or 1 kilobyte size blocks, you can see that memory access performance is actually worse on the Xeon Phi. So it's very important to access memory in a regular way as well. So in some ways, these coprocessors are like an extreme case of making your life difficult in order to get high performance. You have to pay attention to all these things. It can deliver a lot of performance, but getting it can be challenging. Okay, so I'm running a bit out of time, so I'm going to skip the stuff about programming modes and offloading and skip to my final two slides, which is just a few points about how high-performance computing issues are relevant to sparse linear solvers, which we have been talking about for most of this course. And just distilling what I've said earlier in today's lecture, we have many modes of parallelism. So large numbers of cores must be utilized efficiently. Okay, so there's a lot of parallelism, and your algorithms your numerical algorithms have to be able to utilize this amount of parallelism. So for things like sparse matrix vector multiply, that's okay, as long as you're using the right data structures. There's generally enough parallelism. You could be limited by bandwidth, however. But things like sparse triangular solves is not. There's very limited amounts of parallelism in sparse triangular solves, even when you use multicoloring for some problems. So sparse triangular solves are kernels that are much more challenging because of the limited amount of parallelism. SIMD is often hard to exploit for sparse and irregular problems. Okay, so even for sparse matrix vector product, we had to move to complicated data structures. We talked about the LPAC format, jagged diagonal format, and also things like cell C sigma. We need to complicated data structures in order to properly use SIMD. We talked about communication between the nodes as being the bottleneck because the communication to computation ratio is quite high in sparse algorithms, and as a result, people are putting a lot of effort into trying to come up with algorithms that avoid communication or try to reduce the amount of communication that is needed. So a very active area of research over here. And then final 2 points. When you have massively parallel hardware, synchronization can become a bottleneck. So for instance, in cloud subspace methods, you need to do an inner product. That means that all of the processing units have to communicate at the same time to compute this one number, right? So some processing units might be faster or slower, depending on hardware irregularities or because of load imbalance. So, and in any case, when you have this many processing units trying to synchronize, that can become a bottleneck. So there have been some studies that have shown that in GMRes, which has quite a few inner products, GMRes on more than 100,000 cores can spend 70% of its time just doing the inner products. And that is, the sparse matrix vector product, as I said earlier, could be the thing that is the expensive part. But 70% of the time can be just spent on these simple inner products. Machines with accelerators and coprocessors, you may have to adapt your code in order to achieve high performance. So for instance, if you're using Intel Xeon Phi, you really have to use the SIMD units. You have to pay attention to how you access memory. And because you generally have to transfer data across the PCIe interface, again, because you have relatively high communication to computation, that might not be worthwhile unless you're trying to do the entire computation on the coprocessor to try to reduce the amount of communication between the CPU and the coprocessor. Okay, so that's my last slide. Are there any questions on today's material? Okay, so this is also the end of our course. And I just wanted to say that I've been really excited about teaching this course. And it's been both a pleasure and an honor to be your instructor for the past 3 weeks. And I hope that I have shown you some topics and maybe spurred some interest in you in some of these topics that I find to be very interesting myself. Thank you, Professor Wang, for inviting me to come here. I enjoyed, as I said, I enjoyed teaching you guys very much. And in fact, I hope in some time in the future I may be able to do this again. Thank you.
Thank you very much.
Thank you.